Hey there, I'm Dave, and thanks for watching my demo. I wanted to do a real quick demo on hardware interrupts, the use of hardware interrupt signals in programming hardware. And I thought it would be a really good demo to incorporate pulse width modulation, which could also use hardware interrupts. So I created this demo that on the MSP430 processor from Texas Instruments. I'm using today the MSP430 Launchpad, which is an evaluation board from Texas Instruments. For hobbyists that want to create robotics, I'm not sure it's the right platform for you, but for people who want to learn about hardware programming, it's awesome. The reason I'm not overjoyed with it as a robotics platform is because it's not the easiest thing in the world to connect anything to. It's real nuts and bolts. It doesn't come with any pre-made connectors. It just has open ports. But it has some LEDs and it has a clock on board. Some versions of it have accelerometers built in, which could be really useful. Some versions of this evaluation board might have a Bluetooth chipset and stack of software. The one I'm using for this demo is really bare bones. It costs $4.30 from Texas Instruments, and it's just a USB connection, and it comes with a free IAR Kickstart compiler that is really great. The only drawback, it's free, the compiler's free, but the only drawback is that there is a code limitation. So be very careful if you try to take what you're writing in C and say, well, this might work better as a C++ module. Be very careful with that, because you'll quickly blow out the code limit and you'll be stuck with a day or two's worth of work that you can't load onto the evaluation board because the compiler has this code limit. So anyway, I wanted to demonstrate, as I said, hardware interrupts and pulse width modulation. So let's talk about hardware interrupts first. A hardware interrupt signal is a signal that interrupts processing. It's a signal from a device that's external to the CPU, and it interrupts the processing queue of the CPU, and it allows you to execute an interrupt handling routine. And then when that interrupt handling routine is done, it returns to its precise point in the execution queue to continue executing statements where it left off. The alternative to doing things this way is polling. So polling is when you go into a loop and you are continuously checking the state of some device every time you go through this loop. It's kind of similar to if you're expecting a phone call but your phone has no ringer, so you have to pick up the phone every 5 minutes. Hello? Are you there? No? Okay. Hello? Are you there? No. Hello? Are you there? Okay, let's talk. So that can be really inefficient sometimes. So using hardware interrupts is sometimes it's a much better solution. I want to point out that the hardware interrupts can be used even while the CPU on our processor is in a low power mode, or in some cases the CPU can actually be turned off. Meanwhile, the clock keeps running and generating hardware interrupt signals when necessary. So that's another advantage of using hardware interrupts, is that you can conserve power, conserve CPU cycles, and in some cases really just completely put the CPU to sleep while some other part of the processor does its thing. Hardware interrupts are a great way to do pulse width modulation. So let's talk about what pulse width modulation is. Pulse width modulation, or PWM, is a solution to the problem of outputting partial power on a digital port. What's a digital port? It's a port on a processor that can only be turned on and off. There's no 50% or 30% power. It's either on or it's off. In order to simulate 75% or 10% power output on a digital port, we can use pulse width modulation. What that means is we're going to flicker the port on and off at an extremely high frequency, much faster than the human eye can see, much faster than a motor or an LED might respond. And so by flickering it on and off, we can simulate 50% power just by simply having it on 50% of the time and off 50% of the time. Then we can modulate that or output different levels of power simply by changing what's called the duty cycle of that period. The entire length of the duration of the cycle that we're talking about is referred to as the period, and the amount of time that the port is on during that period is referred to as the duty cycle. So I've made a couple little charts here that show you what it might look like to simulate 75% power or 10% power, and I think it kind of gets the idea across. We're going to do this by scheduling some hardware interrupt signals on the clock. The processor, this MSP430 processor, has multiple clock capabilities. One is an onboard clock, and it has another clock port where you might be able to attach. You could go to the store and you could buy a watch crystal, which is a tiny electronic device that you could attach to that port, and it would be much more precise than the onboard clock. The onboard clock is not very precise. After a day or so, you're probably, if you were keeping track of time by that onboard clock, you'd probably go off by about 5 or 10 minutes in the course of a day, which is pretty crude. But for the purposes of doing pulse width modulation, it's perfectly fine, because our cycle is only 300 microseconds or something like that. So let's take a look at some code snippets that I got from some people at Texas Instruments. I've taken these code snippets and I've merged them and modified them and massaged them into a demo where we're doing both hardware interrupt handling and pulse width modulation to accomplish trapping a button click on the device, and each time we click the button, the perceived or the simulated power of the LED is going to increase by 1 increment and cycle through 6 different settings and then go back to off. So this is the interrupt handler and setup code. So there's a few lines of code that need to go into your main function to set up. We're going to set up, in this case, port 1.3 is where our button is. So we're going to enable interrupts on that port, and we're going to clear them so that there's no perceived interrupts sticking around in memory. And then we're going to go into a loop. Rather, it's not really a loop. We're going to set the processor to go into a reduced power mode where it idles and watches for interrupts. Then separately from our main function, we're going to have an interrupt handler routine which watches for that exact interrupt on port 1.3, and when it sees that interrupt come in, it's going to handle that. Actually, it's going to handle every other one, because the button generates an interrupt on a down click and an up click. So each time you click the button, it generates 2 interrupts. So I'm going to filter out one, I'm going to ignore every other one, and every time, on every other interrupt, what I'm going to do is increment the intensity of our pulse width modulation. Now the code that I got, I hardly had to modify it at all for pulse width modulation. It's really neat. We're modulating the LED that's on port 1.6 on the processor, and the first thing we're doing is setting it to be an output port, and then we're setting some options on the port. Then we're setting the period of our pulse width modulation. We're setting the period on the clock as an interrupt, or rather we're telling the clock to send an interrupt signal every 100 clock cycles. Clock cycle is something like 30 microseconds or something like that. Anyway, in clock cycles it's 100, which is good because it's easy to do the math on that. Then we're going to set the duty cycle for 50 cycles. And then we go into, again, a low power mode. It's the same line of code that we massaged from the other one. I think what was really cool in the original version of this demo code, the original author, Mr. Dong, he actually turned off the CPU and let the clock do all of the pulse width modulation processing. So the actual CPU within the processor package went to sleep, but the LED continued to put out 50% power. Just a neat note there. In this case, we have to go to low power mode 1 in order to continue using some other features, namely the button. So let's see how it works. Every time I click the button, it changes the intensity of the LED, and it works almost 100% of the time. So I hope you find this useful. Here are some cool links for you if you want to order one of these devices or something like it. You can go to these Texas Instruments links. And thanks for watching. I hope you enjoyed it.